Hi, I'm Lakshmi Chadrasekaran. I was the science communicator in residence at the Simons Institute this summer. Hi, Yael. Hi, Daniele. Welcome to the Simons Polylogue series. We're very thrilled to have you here as part of our panel. Could you please briefly introduce yourselves for our audience?
I'll go first. I'm Yael Tauman Kalai. I'm a cryptographer. I did my undergrad in the Hebrew University of Jerusalem. Then I did a master's in Weizmann Institute, supervised by Adi Shamir. And then I went on to do my PhD at MIT, where I was supervised by Shafi Goldwasser. So I was very lucky. And then I was in Microsoft for many, many years. And today I'm at MIT. So I said I work in the area of cryptography. Mainly, my research is pretty foundational, so kind of theoretical cryptography and theory at large. One of the main topics I've been obsessed with for the last 15 years was that of delegating computation, so constructing kind of succinct proofs of correctness. But in general, a lot of topics in the foundations of cryptography is what I'm thinking about.
I'm Daniele Micciancio. I studied undergrad in Italy, University of Pisa and Scuola Normale Superiore, and then moved to MIT for my master and PhD, supervised by Shafi Goldwasser. I'm a cryptographer. I learned about cryptography once I was in graduate school. And I've been doing cryptography since then. I'm interested in foundation of cryptography broadly, but there's one specific area that has been the focus of my research during the last 30 years and for which I'm mostly known for, which is lattice-based cryptography. Cryptographic functions based on a certain type of mathematical objects called lattices, which today is being considered as a good way to build some complex cryptographic applications like fully homomorphic encryption, as well as providing a solution to the post-quantum cryptography problem, that is building a cryptography that will be resistant even after a quantum computer is built. So I'm a professor of computer science at the University of California, San Diego, where I've been on faculty since I finished my PhD some 25 years ago.
So I'd like to touch upon both of your backgrounds a little bit before we do a deep dive into the research topic. So we'll go with Yael first. Could you tell us a little bit about what was appealing about cryptography and what captivated you to get into this field?
Yeah, so I'm drawn to mathematics. So I always thought I'd be a mathematician growing up and as a young adult. And what drawn me specifically to cryptography is that I think it's a beautiful way of taking real world concepts and modeling them mathematically. So I view it as a really nice intersection between math and the real world. I like the fact that we're thinking about problems that actually have impact and not kind of made up problems by random mathematicians. It's actually problems that come from basically the world throws problems at us and we use our mathematical knowledge to solve them.
Okay, great. So your work on verifiable delegation of computation allows a weak device to offload any computation onto a stronger device, and it enables that this proof, results be checked efficiently for correctness, right? So can you tell us a little bit about what initially sparked your interest in this problem?
Yeah, so looking back, I would say the first thing that's kind of really drew my attention, or I would say kind of was an eye-opening to me, is this concept of zero-knowledge proofs that was defined and constructed, but originally by Goldwasser, Mikhaili, and Rakoff. And that was like a magical concept that completely changed the way we think about proofs. In particular, they completely changed the model, and as opposed to thinking of kind of mathematical proof where you just verify line by line, they considered this notion of an interactive proof, where now a proof is basically a conversation between, let's say, me, the verifier, and you, the prover, where you try to convince me. And that way of thinking is very different than the way, mathematicians think about proofs and the way they have been thinking about proofs for thousands of years. And this kind of new way of thinking opened the door to kind of, a lot of possibilities. Like what else can you do with this kind of proof model in addition to zero knowledge, which is about hiding, like not leaking information about kind of why the statement is true. And there were like really beautiful results showing that you can do much more in this model of interaction. And that kind of what drew my attention is like, okay, what else can we do? And these early results in the 90s, one drawback, which we didn't think about it as drawback back then, it wasn't thought of as a drawback, but was that, yeah, you can prove much more than you could do like using I would call a classical proof or a standard mathematical proof. But in order to do this proof, in order to convince the verifier using, let's say, an interactive proof, the prover had to work really, really hard. So hard that practically, forget it, it's like not possible. So it was a beautiful kind of, I would say, mathematical curiosity and a beautiful theory, but no way kind of you can ever use it. So basically, the starting point for me in the field is kind of how can we do these interactive proofs, but where the prover's runtime is not too crazy, something that actually can be done, in the real world. And that was kind of the first thing that I've been working on in this field. And then there's been, of course, this field kind of blew up. Now there's so many people working in this field, and there's a lot of questions. And a lot of them are about kind of just certificates back to the non-interactive setting of just kind of, as you said, give me a succinct certificate that certifies correctness of computations and so on. But that was kind of the starting point for me.
Okay, great. So Daniele, can you tell us what captivated you in cryptography and how did you decide to get into this field?
Yeah, so this is a nice question, and pretty much everything that Yael said resonates very much with me. The combination of the elegant mathematics with some problems of practical significance, of course. But there is something. So the answer. So if you ask this question, why did I started doing cryptography? I have to give a different answer. I think in my case, the primary reason was the people, and so. Research is not just about the science and math, of course. That's what it is. But it's also made by people and a community. So when I started my PhD, I didn't know anything about cryptography, and I had no interest in cryptography, primarily because I didn't know anything about it. But when I was there was a really exciting time to do cryptography there. They had some of the top researchers in the world, with Shafi Goldwasser, Silvio Micali, Ron Rivest were there. They also had Adi Shamir or that Goldrake as long-term on sabbatical for 1 or 2 years. And it was at a time when cryptography was, as an academic area, was smaller than what it is today. Today, pretty much every university has a cryptography faculty. At the time, it would typically be 0, the number, or maybe in a few places there would be 1 person doing cryptography. And there were 5 people doing that together with their students. So it was a very, very dynamic community. So I started taking classes and I was fascinated by the topic. But yeah, if not for the people that were in it, probably I would have not paid attention and learned about it in the first place. But then, yeah, the combination, once I discovered it, I learned that cryptography is nothing at all what I was imagining before learning about it. It was this beautiful area that combines mathematics, application in a way that is mathematically elegant, but it also connects with computing practice, with all the relevant problems that come up in securing systems, both in practice for simpler cryptographic primitives, or also things that you can see as potentially interesting and in practice, but in the future you don't even know when they are going to be used in practice, but you know that at some point they will become relevant. And basic research takes a lot of time to develop before something becomes a product and gets used for real. But basic research is what I was interested in doing.
Oh, so that's great. So you mentioned one of the people you worked with was Shafi Goldwasser, right? So, so some of your work with her gave rise to this foundational book on lattice-based cryptography. So if you look back, what would you consider as the most revolutionary aspect of that work?
Okay, so I think the most revolutionary aspect of the work was that we wrote it. So at the time, lattice was a traditional topic in mathematics. It had been studied by mathematicians by more than a century, and there were books on lattices, but they were all mathematics books. Now, when you look at lattices from a computational perspective, what questions are interesting changes a lot. Also, the way the material is presented changes a lot. And there was nothing like a book on lattices from a computational perspective. Those were also the very early days of lattice-based cryptography, which is something that potentially could have been of wide interest within a broad computer science and also more applied community. It was still way far from being practically useful and relevant, but there seems to be a need to try to write something that can help other people to approach, from computer science, to approach the area. So I remember when I learned about the area myself, it was a little bit of a struggle, and perhaps our book helped a little bit. I mean, that's what people tell me, people that read the book. By now, the book is probably grossly obsolete. I mean, so much changed, and the field evolved with also more and more people working in it. But yeah, so it was an introduction. I wish that book had already been written when I was starting, to work in the area.
Okay.
It took some effort, but I think the effort, I think it was some well spent time as well spent, meaning that it was useful to other people, and perhaps this type of writing is something that may be good to spend more time doing those things rather than only writing research papers with new research results. It's something that can be very useful, especially now that the area is becoming more a wider interest, with standardization, interest in using lattice cryptography for many applications.
Right. And you touched upon this briefly. So I'm wondering if you can tell us about, so what are some of the significant challenges in trying to implement lattice-based cryptography for real-world or practical applications?
So one of the challenges is that in practice, in lattice cryptography, there are many different parameters that define your construction. So if you take standard cryptography based on, say, factoring, so the basic underlying problem is, you're given a big number with n digits, bit 1,000, 2,000, 4,000 digits, binary digits, and the problem is to factor it. Now, in cryptography, you want the problem to be as small as possible for efficiency reason, but also big enough to make it harder to crack. In the case of factoring, you just have to deal with this single parameter, the length of the number. So in lattices, the most basic object is a matrix of numbers. And it's not even a square matrix, it's a rectangular matrix, n by n, and then you have to choose also the size of the numbers in the matrix, plus for many applications some additional parameters. And all these numbers, so there is a complex interplay between these numbers, the security of the construction, the efficiency of the construction, and also the versatility. So, for example, in homomorphic encryption, which is an advanced cryptographic primitive where you can compute on encrypted data, So if you use bigger numbers, for some counterintuitive reason, the construction gets less secure, not more secure. But you can perform more operations in encrypted form. So there's a trade-off between the functionality, being able to do more with those numbers, but then you lose in security. But then you can try to compensate in security by using a matrix with a larger dimension. So the size of the numbers in the matrix are bigger. That's bad for security. Then you make the matrix bigger, and that brings security back where you want. But so this, the fact that there are so many numbers to juggle with is something that can be quite confusing in practice. I mean, in theory, you can say that, oh yeah, if you make the numbers big enough, it is secure. That's fairly easy to say that. So in practice, the exact values of the numbers is important for efficiency and practicality. So people really want to put the right numbers there, and there's still today, there is no simple way to work out those numbers by hand. Yeah.
So as we transition into the post-quantum world, can you comment on how you see the ongoing standardization of the post-quantum crypto algorithms such as Crystal's Kyber, as to how this is going to impact the adoption of new cryptographic primitives, because they are in some sense lattice-based, right?
Yeah, they are lattice-based. So standardization has a huge impact in practice, especially in cryptography. And the reason is that in cryptography, you need interoperability. I mean, encryption, as long as you're just encrypting your own data, fine, you can use whatever you want. You store it, then you decrypt it, and you're fine. But in most applications, encryption is used to exchange data securely with somebody else. And you need both parties to use the same system. So if you use different systems, it will not work one with the other. So unless there is a common standard, it is hard to achieve widespread adoption. And if you have many different schemes, even if the schemes are similar, that can be an issue for interoperability. It can also increase the effort of implementing many different schemes. Now, by and large, after all these years of research, we figured out what is the right way to do lattice encryption and signatures and so on. And especially for encryption, essentially, there is just one way to do it. And the standardization was, to a large extent, picking among different variants of the same scheme, or choosing certain set of parameters so that everybody uses parameters that are compatible, plus standardization in cryptography serves two purposes. One is the interoperability. The other one is it works as a sort of seal of approval. I mean, vetting the security of the scheme, which is not something you can test. So for typical applications, you can run it, see if it works. But security is more about what cannot be done, which is breaking the system, that what is done by the construction. And assessing the security of a construction, especially in practice, is not an easy process, and it is also a communal effort. It's something that it is best done by having the whole community looking at the schemes, try to break them, and the standardization process also helps in focusing on specific schemes, so that the attention and the cryptanalytic effort can be more directly focused on some schemes, so that we can gain higher confidence. At the same time, the schemes that are the schemes that get standardized, we are more likely to find vulnerabilities in those schemes than those that were not standardized. Not because we standardized the wrong one, but hopefully we standardize the right ones, and by this effort, will increase our confidence in the security.
Sort of a Goldilocks zone, right? You have to find the Goldilocks zone. Such that it doesn't...
Of attacks? No. The more attacks we try, the better. So that it's not about, oh, we should do less cryptanalysis, so if there is an attack, we will not find it. If there is an attack, somebody will find it at some point, and it is better to find it early than later.
Okay. I wanted to add one thing, Daniele, that you said, which is, I think, also one answer to why adapting post-quantum or not post-quantum cryptographic primitives is hard. Because this issue of interoperability, you need to adapt them together. So, and in other words, nobody cares about post-quantum until there's going to be a quantum computer. That's the fact. People are not willing to work so hard and pay an efficiency or pay until actually there's an attack. And actually upgrading crypto is a hard task. It's not easy. And I think even forget about the specifics of post-crypto constructions, which is indeed an issue, all the things that Daniele said, which is the parameters and that things are very difficult to get right. And there's a lot of parameters floating around. How do you do it correctly? There's just the issue of upgrading crypto in a way that everyone upgrades it and everybody uses it at the same time, and giving people the motivation to do it, that's on its own a hard task.
But we cannot wait for a quantum computer.
We definitely cannot wait.
We can already collect ciphertext without being able to decrypt them, and then
100%.
switching later won't solve it. Yeah.
Exactly. The problem with encryption is, in particular, as opposed to, let's say, authenticity, is that I can store exactly like Daniele said, you can store the ciphertext and wait 5 years, 10 years until a quantum computer will come out, and then you'll decrypt everything. So of course we need to do it. That's no question. But I think it's because the tech is not here today in our hand, it's kind of seems not as urgent.
No, but it's getting a lot of track. There is actually much more there is much more interest in post-quantum cryptography in practice.
Yeah, definitely.
Today than what I would have guessed 20 years ago. I'm really surprised by how the real world is reacting to this potential threat of a quantum computer, which still seems a bit not exactly around the corner. A quantum computer capable of cracking cryptography. But I think there is awareness.
Yeah, but you can see how fast quantum computers grow. I mean, they also make progress, so we need to make progress.
Yeah, no, but progress is, I mean, the standardization, I think, was a fundamental step in making progress. We could have standardized a scheme which is essentially the same as what we standardize now 10 years ago. I mean, we already, with what we knew 10 years ago. We standardized it now because it took a long, when did the standardization process start? I think 2017. So it took, quite a few years just to pick a standard and get some kind of community and agreement. I'm not sure if we reached it, meaning that not everybody was happy about what got picked as a standard because people had different taste or preferences or interest, and but it was not really a competition. The standardization process, and NIST made it pretty clear since the beginning, is not a competition. We can select more than one alternative if we find different ways to build a secure post-quantum scheme. We may as well standardize more than one. And this is what they are doing. So they already standardized one encryption and two signature schemes, and there are more coming, especially for signatures, which is the area where there is more variety between. For signatures, there are actually different ways to do signatures with lattices, and there are also ways to do signatures without lattices, which are all very reasonable, good ways to achieve post-quantum security.
Okay. Great. So shifting gears a little bit, I'd like to talk about homomorphic encryption. Probably a question for Yael. What do you believe is the most promising path to achieving truly practical, fully homomorphic encryption? I think right now it's an emerging technology, right?
Yeah. So first of all, I would say this is a question exactly for Daniele because he's the expert on homomorphic encryption, definitely not me. But if I had to give an answer, I would say one thing that may make it difficult to use in practice, actually there's two things. A, we model the computation when we do homomorphic encryption as circuits, as arithmetic circuits. Thinking of computations and arithmetic circuits is not always the most efficient way to go, and I think that can hinge on practicality. And then another thing is just the way we know how to do encryption today. It has this kind of bootstrapping operation that is very expensive. So just the way, technically, if you look at our scheme, there's an operation there, especially if you want to do kind of deep computations, if you want to compute kind of deep circuits, there's operations that need to be kind of done after every few layers. That's very expensive. Now, maybe we'll be able to get around it and do something more efficient, but currently that's what we know. But I would defer to Daniele.
Daniele?
I'm happy that you went first because I was curious to hear what you have to say. But can you, Lakshmi, can you repeat what the question is exactly that you asked?
So my question is, what do you believe is the most promising path to achieve truly practical, fully homomorphic encryption?
Okay, so the promising path. So I think that with our current state of knowledge, the most promising path is to find the right applications for which what we can do, what we have now, is already efficient enough to be interesting in practice. And then there is ongoing research to try to find substantially more efficient ways to do it. For example, as Yael said, finding a method to do fully homomorphic encryption without bootstrapping, which is this complex operation, which is the main bottleneck. In practice, it's also a theoretical bottleneck. So there's some deep theory behind it. It would be great to do it, but we don't know how to do it. It's something that we don't have any promising path to do that, except for there are some approaches based on indistinguishability obfuscation that kind of avoid the bootstrapping step, but essentially they replace it with something which is even far less efficient. I think that in practice, bootstrapping is something that you can implement. In fact, it is implemented. It is implemented in many open source libraries that you can use in practice. There are companies that are basing their fully homomorphic encryption model on doing bootstrapping many times. So it's something you can do. While if you were to implement encryption scheme based on indistinguishability obfuscation, it probably would be way far from being usable in any practical sense. So yeah, so there are specific things that I think they're promising because I work on those things. The only way to work on something is to convince yourself that there is some promise there. But I don't know when the big step and progress will happen. So there are essentially two broad categories of schemes. One which is based on performing many operations in parallel, so that when you do one operation, you're actually processing a lot of data, okay? And for those schemes, bootstrapping is incredibly slow. It's very costly, okay? Then there are some other schemes for which bootstrapping is much faster and simpler, but they only work on a single bit at a time. They work on very small operations. And there is already work on trying to combine the two approaches or extend the one with the fast bootstrapping to perform more complex operations or to perform many operations in parallel. And there are already some very interesting theoretical results. As it is often the case with theory, the first theoretical advance is something that looks great asymptotically, meaning that it scales well. But if you look at the value of security and efficiency that you're interested in practice, it is still at a point where you don't see the good scaling. So you have this big overhead and the scheme is not attractive in practice. It is promising because it shows that, moving to larger problems, there is a gain. So there is something very, very interesting going on. But there is still a lot of work to be done, and it's not even clear, we don't know if we will be able to do it, but it's fun to try. And so this could be a way forward. There is one third aspect of making things more efficient in practice, which is hardware. So if there is a sufficient interest in performing this type of computations in encrypted form, lattice cryptography in general, and also homomorphic encryption in particular, is highly parallelizable. So it is very, very easy. If you have a bigger chip that can run all the operations in hardware, it's very easy to reduce the time that it takes to perform the operations. And there is already prototype work on hardware support for lattice cryptography and homomorphic encryption. And that also is something that could make a difference in practice.
Okay, great. So I'd like to segue into more general and philosophical questions in cryptography. That's for both of you. So can you talk about what is the biggest gap between theoretical cryptography and its current practical applications?
So first I want to say, actually, I think cryptography is a huge success story in the sense that if you see what's happening today in practice, a lot of the ideas are actually ideas that started in theory and found their way to practice. It's a great, actually, example of like a good productive village working together, where you see people kind of from the very theoretical side all the way to people who are like working in companies and applying these cryptographic primitives, working together to try to make things work, and so I feel like actually a lot of our ideas are already in practice. There are a bunch of theoretical ideas that are just completely not practical today, or maybe will never be. And these are often, when we think about cryptography, we think about question of what is it all possible? What is there even a hope to solve, to construct primitive with properties X? And when someone kind of writes a paper, oh yes, it's possible, and gives a completely impractical solution. So is that really impractical? Yeah, the solution is, but will it guide us to what is practical? Yes. So I think actually a lot of the work we do, even things that you would say they're not practical, it kind of guides us to what the things, where we will go. I do think that usually the things that have a higher chance of getting like more closely kind of on the track to practice are things that are simple. Cryptography today is becoming very complicated. Our schemes are becoming extremely complicated. I'm not talking about the proofs of security. That's okay that they're complicated because that's like, nobody's going to implement the security proofs. But the schemes themselves are becoming increasingly complicated. For example, Daniele mentioned obfuscation. If I want to obfuscate a program, what should I do? Okay, go read one of the papers and try to look at the scheme, how to obfuscate it. Forget it. There's no way anybody can implement it. So whenever things become too complicated, that's when there's no way that they will be implemented. So that's a big gap. However, usually, when things can be simplified down the road. So again, the way I view it in cryptography, it's like a bunch of people kind of layer on top of the other. And if you don't have the foundations, everything will fall. So, I don't view what's practical, the last person who kind of, managed to strip away the last factor X runtime. It's kind of a whole stack. And so I think actually, as I said, cryptography is a really great success story where this stack is actually working well.
Daniele?
So that's very much true, but I would like to add something to it, a sort of different side of the coin. So in practice, especially in practice, and to some extent also in theory, we often think of practicality mostly in terms of efficiency, algorithms, is it fast enough, and so on. Now, and finding solutions and algorithms to achieve certain tasks. But that was, of course, one of the big achievements of cryptography. Most of the work in cryptography is of that type. But there is another thing that was a fundamental contribution of modern cryptography, as we understand it today, which I think is still underappreciated in practice. And that's the fact that modern cryptography gave us for the first time a way to define mathematically what it means for a system to be secure. Okay? And I mean, secure is the name of the game here. If you cannot even specify what the goal is, what are the algorithms good for? Okay. Now, for cryptographic functions, the simpler ones, encryption, digital signatures, through the years, over a span of 4 decades, okay, there is universal agreement about what we should expect and how to mathematically define security, and this is something that is very well understood in practice. Okay, but definitions of security is something that has the potential to be used not only to describe the cryptographic application, the cryptographic primitives, but you could also use that to explain what the final application does. Typically, when a user interacts with a device and with an application that claims to be secure, typically the way that security is marketed is we are using encryption. Or we are using, perhaps soon they will start saying we are using post-quantum cryptography, but that doesn't tell you anything about the security properties of the application. What are you gaining from using post-quantum encryption? As well as I can tell, you might use post-quantum encryption just to encrypt some irrelevant data that you don't care about, and definitions are considered very theoretical. Definitions are not something that you implement, even less than a proof. A proof is something you could still perhaps implement it to have it mechanically checked and get a formal verification of the proof. Definitions are things that are perhaps even more abstract. But I think it's something that could really make a huge difference in practice in terms of building reliable systems with well-defined and understood security properties that are ultimately offered and benefit the user.
Okay, so you both agree that we've come a long way as far as cryptography is concerned, right? So is there any real-world cryptographic system that you find surprising or elegant in design?
Okay, I'll go first here. I have an easy answer. And within lattice cryptography, which is also my area, I still find the most elegant and surprising thing, the most basic construction, which is ITI's one-way function. Is a one-way function first proposed by ITI back in 1996, I believe, which was the first convincing a paper showing that you could do something secure using lattices. Before, using lattices for cryptography was considered a bad idea. And so he built a one-way function, something that is not very useful in the application. Is such a basic object that by itself is not useful by itself. But it is really what opened the door to the following 30 years of cryptographic research, and the construction is very, very nice and simple. It's just a matrix vector multiplication, but with restricted to short vectors. You multiply a matrix by a short vector, and this happens to be a one-way function. If you don't want the input to be short, then you can solve a system of linear equation and invert the function. But when you do Gaussian elimination, when you solve a system, you will find an arbitrary solution. Finding a short one is hard, and it proved that if you pick your matrix uniformly at random, then finding these solutions is as hard as it gets. So it's an ideal, it is the best type of security that you can get in cryptography.
I agree that ITI's one-way function is beautiful, but my answer is different. Even though I agree with your answer too. But for me, the biggest wow is zero knowledge proofs in Fiat-Shamir paradigm. Like the fact that you can prove things in zero knowledge, and that's kind of what governs so much of what's used today is these zero knowledge proofs, together with this what's called Fiat-Shamir paradigm, which reduces interaction. So zero knowledge proofs are interactive, but then you can apply Fiat-Shamir to it to reduce interaction. And basically tons of cryptography, all our communications with our bank, with Amazon, all rely on this kind of very, very beautiful ideas, are just really nice.
That's a great pick too, yeah.
Yeah. So in your estimations, what are some of the biggest open questions currently in cryptography and also in the post-quantum world, post-quantum crypto era?
I think there's a lot of super interesting questions in the post-quantum era, which we don't refer to it really as post-quantum cryptography, but usually when we say post-quantum cryptography, we think of, there's an adversary who owns a quantum computer, and we need to make sure that this adversary doesn't decrypt or our messages or break our systems. But actually, in the post-quantum era, there are going to be some quantum computers out there. That's amazing. Let's use them. And now there's a question: how do we use them securely? How do we take advantage of them? Not just think of them as just adversaries that we don't want to have nothing to do with them. Let's actually take advantage of them. So, for example, how do we verify the correctness of how can a classical computer verify the correctness of a quantum computation? So there's a lot of works around that in the era of post-quantum. So actually kind of dealing with where you actually want to use quantum computers to enhance your capabilities, but you may not trust them. So that's kind of one question. Of course, there's even more long-term question, which is, okay, suppose now we're all quantum computers. Maybe my cell phone is a quantum computer. Now, how do we do things better? That's kind of more when we exchange quantum bits instead of just bits. So that's kind of more down the line. But I think putting even post-quantum aside, I think now the big thing that we should try to think about, us as a cryptographic community, is about securing kind of in the era of machine learning, not just in the era of quantum, but there's now these gigantic learning models, these LLMs, and we need to think about how do we verify the correctness, that they're doing the right thing? How do we ensure robustness of these systems? So there's a lot of really important questions that come up in this realm. Yeah.
Absolutely. And Daniele?
Same question, same answer. The verification of quantum post-quantum in terms of lattice cryptography, how to secure things against quantum computers, there are many technical interest in open problems. But talking more broadly, yes, the post-quantum era opens the door to what can we do with quantum computers, what can we do for cryptography, how does it change what we already know how to do in cryptography, improving. So there's this notion of interactive proofs that is very, very interesting and a huge impact in cryptography. And the prover is classical, well, there's been a lot of work over the years on how to prove that you ran your classical program correctly. Now, if you have a quantum computer and you run a quantum program on the quantum computer, then of course you need something else to prove the correctness of the computation. And there is already research and results of this type, but it's a long way to go. I'm sure there will be more and more very exciting things to come in the coming years.
I want to add one more thing about post-quantum, actually real post-quantum, which is I think it's very important to have more assumptions. Currently, a lot of our assumptions are based on lattices that we hope are post-quantum secure, but we don't know about it. We also don't know about them. We don't know. We assume things. We don't actually know if they're hard or not. We assume. But the lattice one, I don't know, like a couple of years ago, there was an attack posted on our kind of flagship assumptions, Learning with Air. And okay, there was a bug in the paper eventually, but it seemed like it had a lot of really good ideas there. And we were freaking out for a while. So I don't know, I feel like it'd be good to have a few extra options in case something breaks.
I didn't freak out. I had a good night's sleep. I was on my way to a conference in Australia to present a paper, and so this thing came out. By the time I got there, nobody wanted to know about my work. They wanted to know what I thought about that attack. So that attack got a lot of attention. I think it was very good that the person posted it. Yeah. And it was a honest attempt. It was a serious researcher, credible threat, and so on. But it was certainly not the first one. I mean, there were many more things like that that I had seen. Sometimes it was just sent privately to me and to other experts to see if we thought that the attack was indeed valid. And a bug was being found, and nobody would even know that these people were seriously trying to break the schemes. To the point that one of the most frequent questions I was getting from people a while ago was, how do we know that lattice cryptography is secure? Because it looks like that nobody is even trying to break it, because I couldn't find any single paper with an attack. The problem is that we don't have a good way to publish failed attempts. The failed attempts by the top people, it is still hard work, and it is something that is very useful for our knowledge. And so when that happened, it didn't have the same, shock effect that may have had for people that didn't know about the previous attacks. At the same time, it's true. There's always the possibility that an attack is found. And for signatures, we do have already a standard signature scheme that does not use lattices, just based on one-way functions and hash functions. It was standardized together with a lattice-based signature, which is more efficient, exactly for this reason, to have a good backup. It is based on an unstructured problem, a problem that is far less likely to be discovered with some fancy mathematics to have some vulnerability, because it's an unstructured problem. It would be great if we had something similar also for encryption, but there are theoretical barriers in building public key encryption from one-way functions, and that's why for public key encryption we only have lattices. There are a few other problems that are currently being considered for standardization, and lattice is our best bet right now. But having more solutions based on different problems, not just variants of the same problems, is something that would be useful. Even if they don't get standardized, these are important research areas that should get the attention they deserve.
Oh, that's great. So we've touched upon different facets of the post-quantum era. So I was wondering if you could also share your thoughts on what ethical responsibilities lie among the cryptographic community as we prepare as a world to transition into post-quantum computing or post-quantum era?
I think that specific cryptography, so that's easy on the ethical side, meaning that the post-quantum transition is not really making much of a difference. Okay, we have quantum computers. Sure, we want cryptography to be secure against them. I mean, if you talk about cryptography in general, you may have general discussions about the trade-off between the right for privacy for individuals and society, being able to keep society safe. But that's totally orthogonal to the post-quantum angle. So you may ask if there are shall we build a quantum computer at all if it can break cryptography? Perhaps we shouldn't do it. But at the same time, you cannot stop the progress of science. You cannot stop. It's about discovering the knowledge. And you can outlaw the construction of quantum computers. I mean, security is not something you can legislate. Oh, everything is secure by law. It doesn't work. So I don't think that we have any other choice, and there are not. I don't see many issues. I think AI raises many more important and deeper questions when it comes to ethics.
Yeah. I think as if you think about ethics of cryptography, I agree with Daniele. It's not so much a post-quantum or pre-quantum in general. You can ask, what is our ethical a responsibility as cryptographers? And I think at least it should be clear to the users if their data is protected or not. That's very important. People use their data, they post their data places, and they should be very aware on, if their data is encrypted and protected or whether it's out there. For example, when you use Google, when you type questions, or LLM, and you type, the most private questions about your health, is it something that they can then use and be leaked, or is it protected? These kind of things, I think it's important to be very clear about. And I think
so you're saying that we should feel like an ethical responsibility to educate the user?
I think, I think it's, yes. I'm not saying like, it's not necessarily us, the people who are doing the research, but like it should be very important. It's important to be clear when Google should tell us, the users, what are they protecting us or not when we type in our questions? The LLM, when you go to ChatGPT or Gemini, whatever it is, when you type questions, when you ask a prompt, what are they using this data for? And are they using it in a way that protects me or not? I think that's important. Or you know what? Maybe forget about it. Maybe they shouldn't tell the user. They should just protect us. That's it. Maybe I don't care if they say that it should be, our data should be really protected unless it's very, very, very clear that it's not. For example, when you go to the doctor, if you have a disease, you actually need to actively sign that you are willing to release your data for research or for anything. So you're actively aware. And if not, you have the right to not sign. So I feel like our data, in terms of the ethics, our data should be protected unless we sign that we release our data. Now, there's a question, what does it mean to be protected? That's a huge question.
Yeah, what it means to be protected. Currently, cryptography, when you say submit a query to Google, cryptography is used to protect your query as it goes from you to the search engine. Yes. Once you get there, they can do whatever they want with it.
Exactly. Okay, so can they do whatever they want, or are they obliged to protect us? When you go to the doctor, they're obliged to protect your privacy. They can't do whatever they want. They have all the information, but they can't do whatever they want.
But you could also use cryptography to get privacy preserving queries, and you could use cryptography to address the problem to start with using those tools also.
Indeed.
And a lot of people a lot of cryptographers are interested in this type
Yes,
of.
there's a lot of work now on this, indeed. Yeah. I have one more thing that we didn't say, but I think it's important to say. Daniele said that a little bit, but I want to say it more. I think one of the most magical things about cryptography, which Daniele has touched upon, is the people. So Daniele said that that's one of the things that drew him to the area. I didn't know many people, I just came to it kind of without knowing many people, even though I did take Adi Shamir's class and I was really inspired by him and kind of entered the area through Adi Shamir. But really what I want to say, after being a cryptographer for over 20 years, really what's most amazing about the field is the people. I think we're really a fantastic community. We just spent the last summer in the Simons Institute, had such a great time. And every time I went into the building, I really felt like I'm coming home to my family. And I really feel like we're a crypto family.
Yeah, and now, Yael, you are the reason people go into cryptography. No, but I'm saying seriously, and then I thought that it might sound like a joke, so maybe it's better not to say it. No, but I really meant it. Yeah, I really meant to say that. So I'm definitely backing you up. Yeah.
Likewise.
Likewise.
The feeling is mutual.
Well, thank you so much for these lovely discussions. We really enjoyed having both of you here in the panel with us.
Thank you. Thanks so much.
It was a lot of fun. Thank you.